Good afternoon, everyone. I'm Alex Duke, and I'm head of research at Ayrton. That is a design house working in the field of the Internet of Things. We are in France, in Lyon, and we have some expertise in electronic design, RF, wireless devices, cloud application, also machine learning, and we are interested in software-defined radio. And we are also doing research, collaborative research, and the project that I will show you this afternoon is a part of them. So I will try to explain what our motivation, why we want to use software-defined radio, and I will introduce the FED4FIRE Plus H2020 project and the wireless testbed for wireless device, RF and cognitive radio at IMEC. I will show how we can use this testbed, how we can access it and deploy your own GNU Radio software into it. And then I will show the first results of our experiments. So we see that software-defined radio is popularizing and the cost of the device is become lower and lower, and software library like GNU Radio is maturing. I see that there is a lot of interest of SDR in academia, a lot of paper, more and more work, more and more guys are using SDR in academia. And so we would like to use it on our own devices and to put what academia is doing and to put it into industrial and commercial projects. So we would like to use SDR for fingerprinting, passive authentication like for pairing, and also localization. So the main application domain that we are targeting is for manufacturing, for wireless bench or wireless robots, autonomous vehicle in a warehouse, for instance, and also for drone. So we would like to authenticate this device while they are communicating, and also localize them and to authenticate them according to the localization. So for instance, if you have an autonomous vehicle that is moving into a warehouse, we would like to allow it to communicate and to send data only if it's at a precise localization. So we go to the paper and go to the state of the art, and we see that there are relevant papers that is already achieving quite similar tool and quite similar research. And the last one is from the lab where I did my PhD, and we have some guys that's from our team, Thibaut Vial, that also contribute to one of this paper. But however, all of this paper do not study real-world IoT devices. Most of them doesn't rely on conventional communication protocols. Some of them are not reproducible. Others provide dataset, but it is too small to then study them reliably. Others study fingerprinting, but the node doesn't move, so we can't learn localization. And we would like to do our own experiments using off-the-shelf devices, and we need a large test bed and to collect enough data and do it in a reproducible way. So we go through the different testbeds that are available, remote testbed, open testbed, and we see that there is the FED4FIRE Plus testbed, and that is a research project that offer a federation of different kind of testbed across all the Europe. And they also offer a continuous call for SME, so they provide a small funds to allow SME to access the testbed, provide feedback, and do their own experiments on the testbeds. So there are different kind of testbeds that are part of the FED4FIRE Federation, and so different kinds, so wireless testbed, IoT testbed, City Lab testbed, also big data, HPC testbed, and cognitive radio testbeds. And the one that particularly interests us is the wireless iLab testbed that is close to Brussels. That it provides IoT node, wireless node, cognitive radio node, software-defined radio, and a lot of stuff that we could use. So here is a picture of the wireless iLab testbed. So it's kind of a big warehouse where sensor and wireless node are put across the building. So there are two testbeds, in fact. The first one is the wireless iLab one. It's mostly focused on sensor IoT devices. And the second one more focused on the software-defined radio, and they also have Wi-Fi sensor LTE devices. So you can also put your own device into it. You can use it for LTE research. You can put your own base station into it and use the hardware that is already in place. And that's this one that we will use because there are robots, there are USRP and lot device that I will show you a bit later. So for the device that they are, for the IoT device that are deployed in the building, so there are Zolertia with 2.5 gigahertz with ultra wideband. There are also Zigbee, and there are also some other kind of sensor from Nordic Semiconductor, but it's only on the wireless iLab 1 and not on the wireless iLab 2. And about software-defined radio devices, there are different kind of USRP and also FPGA. And all of these devices can be remotely programmed, and you can access them remotely. And so, in fact, each node is connected to a kind of laptop. It's usually an Intel NOC with an embedded PC, and you can SSH to this node, to this PC, and then access the node. There are also different nodes that are mobile. They are put into robots, and you can control the trajectory of the node. So you can collect data and send data while you are moving the wireless nodes. So here is the map of the different nodes that are located across the building. And you can see there's different kind of nodes, and you can select each node. So how you can access these nodes? So first time you can create an account on this web page on the iLab authority. So it's open, and I think that you can just subscribe to it and fill the form, and they will probably ask you for the reason you want an account, what is your project, and then they will approve the account and you can access testbed. The next step is to browse the available device and to book them. So you basically pick the device that you want and you select them and you reserve the nodes during the time you want. And then they provide the software to access then the nodes. That is GFIT, so you install it, you log in, you select the node that you are, and you can then you create the experiment. So you select the node, you set up the image that you want to install, that you want to deploy, and then you can access to a shell, to a remote shell through SSH. So about our experiment, so we use the mobile node and the Nexus 6P device, the smartphone that is on the robot, because we can put into it our own application. So we create an application that is broadcasting Bluetooth advertising packets, and we then collect the data using software-defined radios using this USRP, and we build a basic GNU radio application to collect the IQ data to create our datasets, and we also rely on Belay-dumped project that is an open source code that is demodulating Bluetooth advertising and collect them, and so you can use it then into Wireshark. So here is a basic flow graph. So you see that we put first the IQ data into a raw file for further processing to create our datasets, and on the same time we demodulate the data and create the packet. So we have two outputs: first the raw IQ data, and the second the advertising packet into a PCAP. So now about the scenario of experimentation. So first we have the USRP that is receiving the data and the smartphone that is advertising. The smartphone can move and the USRP, the receiver, is fixed. We then use sequentially the different emitter and at the same position with the same receiver, and then we move them and we can use different receiver. And finally, we can use a different smartphone at the same time to collect advertising for different devices at the same time. So here is a capture of the testbed while we are running the experiments. So we can access to a live camera to see what's happened in the testbed. And here is some picture of the recording of the data, and we display the PCAP into Wireshark. And I think that above it's the remote shell that's connected to the smartphone. So about the next step, we will open source everything and write documentation, so everybody will be able to reproduce this experiment and improve it. We will also publish our datasets and put everything into Zenodo. And then we will try different kind of RF protocol like Zigbee and maybe ultra-wide bands. And we also will use extensively the robots to move all these nodes. Now we have created a dataset, so the next step is to rely on another kind of testbed that is a virtual lab, that is a data center with GPU, and we would like to do some machine learning with the dataset to fingerprint the device, to identify each devices, and also to localize them. And I think that's it. And we will also participate in the stage 2 of the experiment. That is another kind of funding that is provided by the testbed. And if you are also interested in participating to this project, you can apply for funding. I think that you will be happy to have have your own experiments into it and provide feedback to them. So before ending, I would like to thank first the team at the Wireless iLab that is supporting us during the experiments. Also our team at Ayrton. We are in fact 3 guys working on this project. And if you want to follow our updates about this project, we will probably move to the European GNU Radio Days in June in France. I think that there is a lot of advertising about this event during the dev room and during this FOSDEM, but we will be happy to meet you there. So I think that it's time for questions, feedback, comments, and I will be happy to have your your feedback about this project. Yeah.
Okay. Here's the question.
Yeah.
Did you any kind of direction finding and how it's implemented? But the SDR you showed only has 2 RF inputs. Did you with this SDR direction finding of the IoT device?
You mean?
Direction finding. Do you know where the IoT device is located?
Yeah, sure. Yeah.
And how did you do it with only 2 inputs on the radio you used?
2 inputs on the.
The USRP you showed it only 2 RF inputs. Is this enough for direction finding?
So how does the localization work?
Yeah, in fact, we are using the IQ data for that. So, in fact, because we move we can move all the nodes, we can move them across all the building. So, applying machine learning into that. The fingerprint is different according to the localization into the building. So it's not, we don't do triangulation or engulf of arrival or something like that. Yeah. We don't need to have MIMO or antenna array at the receiver for that. Yeah.
In terms of your processing framework, so you showed at the end there a slide of a bunch of servers. What kind of architecture are you likely to go for that in terms of software?
Can you repeat louder, please?
So for phase 2 of your project with your servers, what kind of architecture are you likely to go for in the software? So if I want to write some algorithms, is there any framework that you provide to help with that?
For doing what? For the
you have your stack of servers at the end there, presumably to do some IQ data processing, right?
Yeah.
Do you provide any software framework to assist with that process?
Not yet. Not yet. In fact. Yeah. Yeah.
Do you plan on fingerprinting
Sub-gigahertz sensors? I think that it's on our roadmap because there are some sensor in the I think it's 800 megahertz. So I think that we can try it. Yep.
Do you plan any real-world validation of your results afterwards? Because your results may be very specific to the environment that you're testing.
Yeah. It's on the second. The next step is to develop algorithm and everything and validate it in the test bed, and then our goal is to move it to the real world. Yeah.
Are there any other questions? Seeing none, let's thank Alex again.
Yeah.